We now consider a function whose formula we don't have, but for which we have a number of data points. And we're going to use our new estimate techniques, in particular the trapezoidal rule, to estimate the integral between 0 and 10 of this function. Now I think it really helps to have a quick diagram of the function itself here. We've got points at 0, 2, 4, 6, 8, and 10 in terms of x. And the values that it takes on, that the function takes on, are 1, 3, 4, 5, 4, and 2. There we go. So if we were to do a trapezoidal rule estimate of this area underneath this curve, so this is the function, but if we're trying to do an estimate of the area beneath it, or its integral, as indicated here, we'd be trying to find the area of these trapezoids. And so the integral from 0 to 10 of our function, we don't know what the actual function looks like, of course. The function may do something like this, it may do something crazy, we don't know. All we know are the landmark points at these particular x values, so we do the best we can with what we have. And we say that this integral is going to be approximately equal to a trapezoidal estimate. Instead of the integral of the function, we're going to approximate it with trapezoidal approximating shapes underneath the curve of the actual function. And here we have 5 intervals, so we just call this the trapezoidal rule with 5 intervals being used. Now that rule there is, well, it's going to be the area of each of these trapezoids. I'm not going to put the general formulas, you have those earlier. I'm going to jump straight to using the function values we have. The only thing I'm going to pre-calculate here is delta x. Every interval here in the x direction is an interval of size 2, so we'll use that. So on the first interval, we have a y value of 1 and a y value of 3, and the trapezoidal rule says take the average of those and then multiply it by delta x. On the next interval, we have 3 and 4 as our heights, and we multiply that by delta x. We'll bring the delta x equals 2 in later. On the next interval, it's 4 and 5, and then it's 5 and 4, and then it is 4 and 2. So that would be the most straightforward way to associate the trapezoidal rule with 5 intervals with the direct calculation. Now it's worth pointing out that we could have done this a little more easily. We could skip this step and jump to this alternative form, which is sometimes faster to calculate with. Notice the associations we have here. We have a 3 twice. We have a 4 twice. We have this 5 twice. Oops, there we go. 4 twice. So that pattern we saw in an earlier set of notes can be drawn out here. We have the single 1 here, once. We have 2 3s. We have 2 4s. We have 2 5s. We have 2 4s. And we have one last 2. Oops. Try to circle that in red too. Or there's the list of numbers that we just used. 1, 2, 3, 4, 5, 4, 2. And with that list, the thing that we haven't accounted for yet was the delta x, and every term had a 2 in it, or a half rather, had a 2 in the denominator. And this form here is often much easier to calculate with than doing all these fraction work. Here we have 1 plus 6 is 7, 8 is 15, 25, 33, 34, 35. 35 times delta x, but delta x is just 2. And that gives us 35. So the integral, that's approximately the area underneath the curve of f of x dx, or the integral, more precisely, of f of x dx on the interval from x equals 0 to 10 is about 35. So that's a nice concrete example of the calculations we can do with the trapezoidal rule. if we hadn't been given these values in a table, if we'd been given a formula, we would just fill in the table ourselves first and then do the trapezoidal rule calculation. Last but not least for this unit, let's consider a more abstract idea. Trying to sketch the graph of a function f of x on the interval 0, 1, so a nice well-defined interval, for which f of x is decreasing, so it's heading down, and for any number of intervals we choose, so we're looking for a general property of the function so that the midpoint is always larger than the integral value, the exact area under the graph, and the trapezoidal rule is always less than. Now, some people have a temptation to just start sketching graphs like crazy and saying, well, hey, what is that? What happens here? What happens if I do that with midpoint and trapezoids? I would not recommend that. I would not recommend the shotgun approach. I would start off as simple as possible and just see, hey, maybe there's an easy answer to this. And in particular, if we look at the kinds of patterns we've seen on the derivative side, if we have a decreasing function, it could be linear, or another simple shape might be concave up, or another simple shape might be concave down. And if we explore each of these, we can see maybe how the midpoint and the trapezoid rule play out. Well, for sure, linear is not the answer, because we actually saw earlier that if we use a linear function, then the trapezoid approximation is in fact not an approximation. It's exactly equal to the integral. So that would be an exact thing. So that's not what we want in our case. Let's do the trapezoid rule again. Here, we'll do a bunch of points along the way. If we do the trapezoid for concave up, it's a little subtle, but we can see that, well, let's zoom in a bit here. If we had a trapezoid and an interval where the function was concave up, the trapezoid rule would definitely be larger than the actual integral from 0 to 1 value. So that's not what we want either. All right, well, if in doubt, let's go to the last one. Let's try just doing it at 2 points here, 2 intervals. Aha. Now if we look at this function and ask how does the trapezoidal rule relate to the actual area underneath the graph, or the actual integral value, here we'd have that the trapezoidal rule is going to be less than the actual integral. All right, so that's good. That's what we like. And next, does it actually work the same way? Do we get a free lunch here where we pick our intervals and try to look at the midpoints. Midpoint. And I think it's a little more obvious on this second interval, but it would be true here as well. This area is an underestimate for the midpoint. This area here is an overestimate for the midpoint rule. Overestimate for the midpoint rule. And because of the curvature, we can see the midpoint rule puts us higher than it would be if we were following a straight line, because it bends more down after the midpoint. And so the underestimate is going to be smaller than the overestimate. And that means that our midpoint estimate with n intervals is going to be larger than the actual integral value. So that's a little bit of insight just to work through how these sketches might affect our interpretation or understanding of these different rules and the relationship between those rules and the exact integral value. But if we're looking for a function here that would satisfy the constraints here, decreasing and for which the midpoint rule is always larger and the trapezoidal rule always produces a lower than the exact estimate, then anything which is decreasing and concave down we already know it's decreasing, we were told that. But any function which is decreasing and concave down will satisfy the requirements. And that pretty much concludes our introduction to the numerical techniques for evaluating integrals and approximating integrals with calculations. We're going to resume, say, a more traditional study of integration in the next unit.